Hello, myself Professor H.K. Bangale from Department of First Year Engineering, SMD College of Engineering and Research Center, Evla. I welcome you in a video lecture series of Basic Electrical Engineering of First Year Engineering course. We are discussing about the DC circuits. In part 5, we will discuss about Kirchhoff's voltage law. We already discussed about Kirchhoff's current law. Now let us proceed for Kirchhoff's voltage law. So the Kirchhoff's voltage law states that the voltage around a loop equals the sum of every voltage drop in the same loop for any closed network and equals to 0. Suppose this is a closed network. Okay, this is a closed loop, and in this loop, the voltage around this loop, means voltage across each element in this loop, voltage drop across each element in this loop. If we add it, we take the sum of every voltage drop across every element in this closed network, then it always equal to 0. And this is nothing but your Kirchhoff's voltage law. The sum of all the voltage drop around the closed loop is equal to 0. So here voltage drop across the resistance R is noticeable AB. Voltage drop across this is VBC, it is VCD, and it is VDA. So the sum of all these means VAB is equal to VBC, VAB plus VBC plus VCD plus VDA, that's equal to 0, and it is nothing but your Kirchhoff's voltage law. So now, while taking the sum of all the voltage drop across each elements of any closed loop for Kirchhoff's voltage law, that time what sign convention to be taken? So that is a question mark. And generally there is always confusion or taking the sign. Whenever a voltage source is given, EMF source is there, then what should its sign? If a resistor is there, then across its resistor, certain voltage drop is there, then what the sign to be considered? Okay, so let us see this sign convention. So whenever there is a current direction is like this, means positive to negative, current flows from positive to negative, right? Means here is what happened, here is the drop in potential, there is fall in potential is there, and whenever there is fall in potential, it is always considered a negative voltage. So whenever there is a fall in potential or drop in potential, that time always give it a negative sign. Whenever it is from minus sign to positive sign, current flowing from negative to positive, that time there is a rise in voltage. There is a rise in voltage, a rise in the potential, and that rise in potential is always taken as the positive voltage. So remember, whenever there is a flow of the current from positive to negative, that time the drop in the potential is there, voltage drop is there, fall in the voltage is there, and that is negative sign. When your rise in voltage is there, that time it is considered as a positive sign. So you remember this sign convention. Now, this sign convention, now when if a battery is there, voltage source is there, and you are traveling directions from negative to positive. When you are traveling from this negative to positive, that time which sign to be taken? It is always from negative to positive means what? Rise in voltage. So here in first case, when negative to positive is there, rise in voltage. When rise in voltage is there, that time positive voltage should be taken. So here I am traveling from this direction, that is from negative terminal to positive terminal. That time there is a rise in potential, and that's why it is always taken as the sign of this battery source. E is always positive. Now here I am traveling from positive terminal to negative terminal, means there is a fall in potential, and this fall in potential is always taken as negative. So it is negative. So remember this. Now for sign convention for resistors. So here again the resistor, we are traveling in this direction. We are traveling in this direction opposite to the direction of the current. We are traveling, current direction is like this. Like this means from right to left, and here it is left to right we are traveling. So whenever we are traveling opposite to that of the current, that time That time means we are traveling from negative to positive, means there is rise in voltage. When a rise in voltage is there, that time this voltage drop across resistance is IR, it is always taken as positive. Now here in this case, we are traveling in the direction of the current itself. We are traveling in the direction of the current itself. Means that time we are traveling here from positive to negative terminals, mean there is a fall in potential, fall in voltage drop is there. So the voltage drop across this resistance, that is IR, is to be taken as negative. So remember this sign convention. Now here is the same, using this Kirchhoff's voltage law, consider a branch which form part of a loop. So let us say it is a one branch of any of the loop, right? It is a part of the loop, and we are moving in this direction in this loop, okay, from positive to negative. So V1 voltage drop will be there. So this voltage drop is there. Okay, positive and negative means there is fall in the voltage. So this fall in voltage is always taken as negative, and here is we are moving from negative to positive. So voltage rise is there. Voltage rise is there. Negative to positive. So it is always taken as positive. Rise in voltage, positive. Okay. So the formulation for Kirchhoff's voltage law. So the first formulation we can state that the sum of the voltage drops around the loop is equal to sum of the voltage rises around the loop. Second formulation we can say that algebraic sum of the voltage drops around the loop is always zero. The time voltage rise are included with a minus sign. Third formulation we can take that the algebraic sum of the voltage rise around the loop is equal to zero, means that time voltage drop are included with a minus sign. So it is a conservation of energy in a loop. The KVL, major implication of the KVL tells us that any set of the elements that are connected at both ends carry the same voltage. What is it? Any set of the elements that are connected at both ends carry the same voltage. Means these are in parallel. So we say these elements are connected in parallel, and whenever they are in parallel, that time the voltage drop across that element is the same, but the current flowing through them is different. So apply KVL in the clockwise direction. Clockwise direction means like this we have to move. In this direction we have to move clockwise. Okay, means like this we have to traverse in this loop. So applying KVL in the clockwise direction starting at the top. So it is plus 2 minus VB. Means here is what happened? Positive to negative. Okay. So VB here negative to positive means rise. Okay. So this VB minus VA is equal to 0, or otherwise VB is equal to VA, and VB is equal to VA because there is both are connected in parallel and the voltage drop across them is always same. Okay, so here are the three closed parts you are observing in this network. Very first closed part is the first loop. This is second loop and second closed part, and third one is this one outer. Okay, so here is the outer part. So for this 1, 2, and 3 loops, we can formulate the 3 equations. Okay, the 3 equations we can formulate for part 1, for part 2, and for part 3. Okay, so for this we can formulate the equations. Okay, so if we move in this direction, then here from positive to negative. So what is the sign convention for positive to negative? We are moving from positive to negative, means there is, what is there is? Fall in voltage. Here is fall in voltage. Again here positive to negative means fall in voltage. So it should be taken as negative. So minus V2 minus VB. Here negative to positive, rise in voltage. So it is plus VA. So it is V2 minus V2 minus VB plus VA is equal to 0. So in the same way you can formulate this. equation for another two loops. So no time varying magnetic flux through the loop, otherwise there would be an induced voltage. That is the Faraday's law. Okay, so an underlying assumption of the KVL. So note, the antennas are designed to pick up electromagnetic waves. Regular circuits often do so undesirably. So avoid these loops. Whenever such loops are there, so avoid that. So your resistors are in series. So these R1, R2, R3, and R4, these four resistors are in series. So consider a circuit with a multiple resistors connected in series and find their equivalent resistance. So the equivalent resistance you can find as R1 plus R2 plus R3 plus R4. And whenever these resistances are in series, that time voltage drop across each resistance is different, but the current flowing through each resistor is same. So the KCL tells us that the same current I flows through every resistor, but KVL tells us that voltage drop across each resistor is different. In resistor 1 R1 it is IR1, in resistance R2 the voltage drop is IR2, in R3 resistance it is IR3, and in I4 resistance it is IR4. And IR1 plus IR2 plus IR3 plus IR4 is equal to equivalent resistance. Okay, voltage drop, this voltage drop can be added. Okay, so I will get cancel and we will get R equivalent is equal to R1 plus R2 plus R3 plus R4. So get resistance of a resistors in series is the sum of the individual resistances. So you remember this. Okay, so here the voltage, it is also a voltage divider circuit. Okay, so here voltage get divided into V1, V2, V3, and V4 like this. Any number of resistances you can add, and your this VSS will get divided into that much number of voltages. So this series resistances can be used as a voltage divider. So here is our voltage divider. V2 we have to find, and V2 is equal to R2, the resistance across voltage drop across R2, that is V2, that is R2 upon R1, sum of all these R1 plus R2 plus R3 plus R4. So for this we can find out the, or it is correct if we nothing else is connected to the nodes. But here we can't apply this voltage divider formula because the R5 is there. Okay, so it is, these are not in series. Okay, so only for series circuit this formula is applicable. Here the resistances are in parallel, current flowing through them is different, and the voltage drop across them is same. So the KVL tells us that the same voltage is dropped across each resistor R1 and R2. Okay, that is Vx is equal to I1 R1 is equal to I2 R2, and KCL tells us that the currents are different and they are divided into two parts, that ISS is divided into I1 plus I2. Okay, then the general formulation. So what single resistor R equivalent is equivalent to three resistors in parallel R1, R2, and R3. That is equivalent resistance is R equivalent, and the reciprocal of the R equivalent is equal to reciprocal of R1 plus reciprocal of R2 plus reciprocal of R3. So equivalent conductances of resistors in parallel is the sum of the resistances, reciprocal of the resistances. So thank you. Next time we will see the next topic. Goodbye.